All right, so here's a problem for class 20, the first example problem applying Newton's second law to a rigid body. The flywheel shown has a radius of 20 inches and a weight, right, weight emphasize, of 250 pounds and a radius of gyration of 15 inches. A 30-pound block is attached to the wire that's wrapped around the flywheel, right? So this is almost acts sort of like a drum. And the system is released from rest. Neglecting the effect of friction, determine A, the acceleration of block A, and B, the speed of block A after it is moved 5 feet. So one of the housekeeping things we can get around to is we could figure out what the mass moment of inertia of the flywheel is going to be. That's going to be m mass times the radius of gyration squared. Make sure that we're using everything in feet and slugs. So we take 250 pounds and divide it by 32.2. So that's the mass now. And then we take the radius of gyration, 15 divided by 12, and we get 12.13, and that's going to be slug feet squared. Now I want to draw, and the all-important, so very important, FBD, IBD diagrams. And here's going to be the first time I think we introduce some of these ideas. So it's important. Let's see. Let's define our directions. So we have everything in terms of the diagrams, but let's put in all the forces on the left-hand side. So we're going to have reaction forces right here. At B, I guess I decided to call this B. And so this is going to be, sometimes I use R, but I'll go FBX and FBY. And some of the other things we have on there, let's put a green. We have the weight of A. We also might have the weight of, let's just call the whole thing B, that's acting right down there. Now, in terms of acceleration, on the other side, we're going to have the mass of A times the acceleration of A. We're also going to have the mass moment of inertia of, let's call it B, times alpha B, right? And one thing we could do now is we could link some things up between, we could call it dependent motion, or we could just call it kinematics. We happen to know that the acceleration of A is going to be equal to the angular acceleration of B times RB, right? Because a point right here is going to have a tangential acceleration in that direction, where it's going to be, so we're actually combining some kinematics already right in there. Now we want to write out the equation for this, and I'm gonna put it over here onto the side, even though I like to put it underneath it. That's okay, I'll put it underneath it. I want to put the sum of the moments, and I want to take it about B, because I don't want to use this reaction force. I don't know them yet, so I want to circumvent them. So I'll take the sum of the moments about them, and I say that it's going to be equal to the sum of the moments about B that are the effective moments, right? So here's where that idea of the effective moments come in. Those effective moments are going to be I times alpha, but also, and so here's the thing that that's an important concept, or the reason why that we're going to write the effective moments, is that this mass times this acceleration makes an effective moment, right? It makes that the mass times acceleration times the distance right here is going to be an effective moment. Now I should have, because of the direction things were moving here, this should have been negative right here, right? Because I said that positive was counterclockwise. So that's going to be a negative I about B, alpha B. But also, this mass times acceleration right here, it is also going to be negative. But it's going to be a moment. It's got to be an effective moment. So that's just mass time. That's just an effective force. We have to multiply it by RB right there in order to get this to be true. Now, something that we're going to notice that's going to come up right here is that we already have this relationship that's taking place. So we can substitute the acceleration right there. And so plugging numbers into this right here, we have negative, this 30, this is equal to 30 pounds, times its moment arm, which again is going to be right here. That's going to be the moment arm that's acting right there. And that's 20 inches, because it's the radius right there. It's going to be equal to negative. And by the way, that was this one on the left was also negative because it was clockwise. The mass moment of inertia is 12.13, and we don't know alpha B, minus the mass of A, which is going to be 30 divided by 32.2 times alpha B times R, but it's alpha B times RB, right? Which was 20 over 12. But also times 20 over 12. So it's really R squared right there, right? Because we had an RB from here and we have an RB from right there. With this, we can find what alpha is going to be, and we get 3.397 radians per second squared, and we know that it's clockwise. So if we want to get the acceleration of block A, we can go back up to this equation right here and say the acceleration of A is going to be equal to alpha B RB, or 3.397 times our 20 over 12. And that's going to end up being 5.662 feet per second squared, and it's downwards, right? So if we're going to write that, we should put a hat on top of him and say that this is going to be the answer. We should really write it out all the way and then box it. So that's like a complete answer because it has the arrow in it. Now if we want the speed of A after it has moved 5 feet. Okay, so what do we know about this acceleration? Is it constant or not constant? Well, does any of the moments change that are here on the left-hand side? If none of the moments change, then the alpha has to be the same. So that means that the acceleration has to be the same. So it's a constant acceleration. And since they give us a distance, we can go V squared is equal to VO squared plus 2A and then delta. And I guess these are Y. So we could actually put them Y on top of all of that. So we could say that the velocity is going to be equal to the square root. This is 0 squared. It starts from rest plus 2. And if we want to keep the directions the correct, we go negative if we want 5.662. But it does move downwards in a negative direction. So it's moved down 5 feet. So it ends up being, this ends up being 7.525 feet per second. So V of A is 7.5 0.25 feet per second downwards. And we have answered the question now. Ta-da!